Okay, this is lecture 22, and we're going to go into part two of lecture 22. And we're going to be specifically delving into the idea of design storms. And this is going to give you a quantity or a rate of precipitation for various frequencies and durations of rainfall. And then we're going to have to distribute that in time because just knowing a quantity doesn't allow us to do any modeling and understand kind of the rainfall runoff process. And then I'm going to touch on a concept of extreme value of storms or extreme values. When we talk about these design storms, we're talking about usually of some frequency of occurrence. And so we have the 1% annual exceedance probability, which is also known as the 100-year rainstorm. We have the 500-year rainstorm. We have the 1,000-year rainstorm. We have a 2-year rainstorm. It's a design frequency. When we talk about extreme values of storms, we're talking about what is the outer value of what is possible in order to have happen. And we use this for really what's the word I guess I'm looking for? Really. Designs that you really cannot allow them to flood. So when we think about nuclear power plants, when we look at high hazard people that would be killed downstream, or in the case of a nuclear power plant, kind of the environmental and death that would result from having a mishap at a nuclear power plant. So when we think about design storms, this is a slide from the previous lecture 21. We're looking at an intensity or an amount, and this intensity is a depth per time. So that's where we talk about the IDF relationship. So we've got intensity is one of those terms. I'm sorry, we got a duration, and we got a frequency. And so this D here is not the D that we have in the IDF relationships. That D is a duration. So when we think about it over some duration of time, and so when we look at this, and I know it gets confusing when we talk about the IDF relationships, but just keep that in mind. Frequency typically expressed in terms of return period, TR. I mentioned this last time, but the probability is equal to TR. So when we talk about a 100-year event, TR equal to 100-year, what we're talking about is that probability is 1 over 100 or 0.01 or 1%, okay? So return period then is defined as statistically, it's a statistical average length of time in which the given quantity will be exceeded once. All right, so here we've got, 100-year, 2-hour rainstorm. That means that on the probability, 1% chance or 1% probability that in any given year, at that location will experience a 2-hour rainstorm of 6 inches or greater. All right, so we call these the IDF relationships. That's what I was telling you earlier. You can get these from maps or equations, and there's a number of ways to do it. At this time, we have advanced through a number of different publications in 40s, 50s, 60s, 70s, 80s. Atlas 14, which is a very nice web application that allows us to do everything but the Pacific Northwest to get these IDF relationships. And so this is an example. This is 1961. This was what's called TP40, which was Technical Paper 40, which was introduced by the Department of Commerce Weather Bureau, which was the precursor to the for the United States. And you can see this is in this publication, there were a bunch of these different maps. They would have some frequency and then some duration. So for the 100-year I think they had like a 2-hour, 3-hour, 6-hour, 12-hour storm. So this is the 1-hour storm values for the 100-year flood or the 100-year rainstorm. You know, they would have a map, a series of maps for the 50-year frequency, and they would have, you know, 1, 2, 6, you know, I'd have to look it up, but they'd have all these various frequencies, I'm sorry, durations that would happen. And so this is for the 100-year 1-hour rainstorm. And you can see here that we've got isohyets of equal precipitation. And so I've highlighted the 3.5 inch, means that for the 1-hour duration and the 100-year or the 1/100 probability, this is the 1 or the 3.5 inch. Looks like I got off the line there a little bit. And so here we are in Phelps County. Redone the frequency statistics, but if I would have been doing a design in 1970, say, this would have been what I would have used, that if I was running an analysis, I would look at the 100-year 1-hour rainstorm, a depth of 3.5 inches. So there's a lot of outdated, some of these are older publications, outdated. As I mentioned, there's TP40, there's Hydro 35, there's TP49, and all these different things. And there's a number of other reports as well. You know, TP40 did the entire United States and did from a 30-minute duration up to a 24-hour duration, and from the 1 year to the 100-year rainstorm. Hydro 35 basically looked at less than 60 minutes. So, you know, the TP40 looked at 30-minute to 24-hour. This goes down all the way. And it looked at, you know, from 2-year to 100-year recurrence interval. TP49 looked at 2 days to 10 days. So this is, you know, large rainstorms over a number of days. And so all these publications are out, no longer applicable because NOAA Atlas 14 has replaced them. And so if you look at NOAA Atlas 14, this is the map that tells you where the relationships are in terms of you know, what states that are applicable with NOAA Atlas 14. So you can see the only states that don't have NOAA Atlas 14 are those in the Pacific Northwest. And you can actually look here and see, okay, by state, you can look at, okay, this is my duration. So these are less than an hour. This is hour to 24 hours. This is see most of these, like Alabama, they're all NOAA Atlas 14. Now there are various versions. There's various reports out in NOAA Atlas 14. They're all part of that web base, but if you wanted the web point and click, you know, sort of a graphical user interface, a map interface, but if you wanted to get the details on how they were done, you would actually look at, you know, this is volume 9 for Alabama, volume 7 for Alaska. If you go down here, we're in Missouri, we're in volume 8. But let's look at a state like Idaho that is not on the NOAA Atlas 14. So you can see that for less than an hour, they used a report called Arkell and Richards, 1986. And for 1 hour to 24 hour, they use NOAA Atlas 2, which is not NOAA Atlas 14. And then they use TP49 for greater than 24 hours. So let's click on that. That gives you a little more of a blow up of that. And so if I clicked on the Arkell and Richards, it would take me to a paper by Arkell and Richards, and this is the less than 60 minutes. And you can see there they're using ratios, and so they're using ratios of the what was in NOAA Atlas 2. Remember that NOAA Atlas 2, if you recall, was for that 1 hour to 24 hours. So they're basically using a ratio to get these various values depending on where you're at, whether you're central northwest, interior northwest. This is for the northwestern United States. So, you know, California is no longer part of this. You actually have NOAA Atlas 14 covering that. But if you're in an area in the Pacific Northwest, coastal or interior Northwest, you would be in these two areas right here. So you would apply a ratio to whatever you have in NOAA Atlas 14. And so you would read through the report and get that information. This is NOAA Atlas 2. I'm sorry, did I say 14? I meant to say NOAA Atlas 2. If you would look at NOAA Atlas 2, if I clicked on that link, this is NOAA Atlas 2, and you see a series, when you go to that atlas, you see a series of maps. And here I've got in tenths of an inch. So if you were to zoom in here, you'd see, you know, that's a 15-inch, 14-inch. So again, this is a 6-hour precipitation. They can get some serious rain out there in terms of their probability statistics in that location. So if we look at you're going to have to do this for some homework problems. You can see this is the link for that, and you can notice here with this cursor, you can move the cursor. It'll pop up, you know, when you get to this, and you should look at this soon. You'll be able to move this cursor around, and you can move it anywhere you want. And as you move through, I've centered over Evansville, Indiana, and this is what the table, if you scroll down, that looks like this. You can have a table, or you can also do a graphical output as well, and I'll show you that in a second. But you'll notice that down this column here is the duration. So this is the time. It goes from 5 minutes down to 60, quite a spread in terms of time. And then you've got the recurrence interval. This is in years. So this is this TR that we've been speaking of. And remember that the annual exceedance probability is equal to 1 over TR. We also called this just the probability, but this technically is called the annual rainstorm for 5 minutes. You'll notice that for the 100-year rainstorm, that's 0.843 inches. You'll also note that there's some information here in parentheses, and that information in parentheses is explained down here in the bottom. The 90% confidence interval. And that means, if you recall from statistics class that you've had, that means that we're 90% confidence, we have 90% confidence that the true answer and 0.919. Obviously, the larger this range, the less confident we are in our statistics. So that, you know, you should always look at this when you look at the any kind of statistical data, the confidence in terms of assessing how good the data fit the probability distribution. If it doesn't fit it very well, then these confidence intervals grow in their distance, and so you can also do entered in 0.57 versus the 0.83 versus entering in 0.919. So you kind of get a range of rainfalls there, and you can kind of get an idea of the sensitivity of your modeling or whatever you're doing to the rainfall data you get. So that's kind of a tour through the NOAA Atlas 14. If I were interested in the 2-hour rainstorm, 100-year, it's 3.85. If I were interested in the 24-hour, it's 7.15. And again, you're going to have homework assignment to go through and look at some of these things. You're going to pop up these two graphs. And again, this is precipitation depth in inches. This is duration. And you can see here's duration plotted. And then the colors are the various recurrence intervals. If I wanted to plot the colors being in duration versus the recurrence interval down here, I can also turn it on that way. Now, one thing I want to mention to you, this is in terms of depth here in inches. We also have the ability to change this over and show, instead of up here, instead of showing precipitation depth, I can get an intensity value that would give it to me in inches per hour. So make sure you remember what you're doing in terms of how you're requesting your data. All right, one thing we get into, like rationale method for rainstorms and things like that, we're going to want a time of duration that is possibly less or not, that fits one of these standard duration times. And you can see the standard durations. But let's say that you were in need of something else. You were needing something that maybe you know 3 hour and 6 hours what you had, but let's say you needed 4 hours, and so you could go in data and you can interpolate between the two, and that's what we're doing here. You can see this particular one is I don't know if it's interpolated or what, but this is a 5-year recurrence interval. I think I made this one up on some other things I was doing. I'm just kind of which is given to me to estimate what my 4-hour duration value would be. And I've also used the IDF plots. This is from a flood that I've already lectured you on in lecture 11. This is the Arkansas data looking at precipitation depth and annual exceedance probability and for various durations. And you can see how the data plots here. This is a 120-minute storm. You can see that that was somewhere in 5, 6, 7, 8. It's about an 8% annual exceedance probability. If I just look at the 120-minute, you can see if I look at the 6-hour, then it starts to come a little more rare, which is 2, 3, 4. Looks like a 4%. Six-hour. This is my 3-hour over here. You can see there that's a 2% annual exceedance probability. Again, this is a log space, which is a TR equal to 50 year. So depending on how long you're looking at in terms of your time duration, your frequency of that rainstorm will change. And this is just a way to kind of characterize the rainfall in terms of what kind of, how rare the event was. I want to mention to you that Bulletin 71 for the Midwestern states, I give a shout out to colleagues at the Illinois, Champaign-Urbana, Illinois, located at the University of Illinois. You may be asked in terms of a stormwater ordinance to actually use Bulletin 71 to pick your rain values instead of NOAA 14. I don't think that's going to happen too often, but you might be. One thing about to be talking about Huff's distribution of rainfall to get a time series. That's contained in this Bulletin 71 as well. And so TP40, and I put this in here just to kind of remind you, even though that we no longer use TP40 for most of any kind of analysis we do for rainfall, it's just to give you a look in terms of these area depth curves. And the interesting thing here is if I've got, basically a point, my area goes down to a point, so it's 0 right here. If I've got a 30-minute rainstorm and I start to then say, okay, what's that look like if I've got against what I've got for if I increase my area. And you can notice that if I go to 50 square miles or 100 square miles, then I become basically down around, let's say if I'm at 100 square miles, I'm looking at basically about 62% of what are for that data that I've got for 30-minute data at that point. So if I'm trying to extract the point data and use it for an aerial estimate of the rainstorm, you can see that it really degenerates and cover more and more area. The way rain works, it's not going to be uniform in its distribution. And so when you try to fit statistically looking at things or trying to take a point value and estimate how that translates into happening over an entire watershed of some size, we have to know that value is going to decrease. So when we look at so that's getting actual values of depth based on duration and frequency of occurrence, but we need to distribute that. Now, I've kind of updated this lecture, so if you've looked at old lectures of mine, I've kind of concentrated on these two methods, the Huff and Angel method for distributing rainfall and the USDA SCS method. But this method now references in Canvas, as you can look at the NRCS National Engineering Handbook on Hydrology, and you go to chapter 4, which we're going to talk about in a second, and you'll see that they've recommended that you means that for NOAA Atlas 14, that's for most of the country except for the Pacific Northwest. Now, the Huff and Angel method, that's still applicable. People still use it, and you can find that in this 1992 publication, Rainfall for West. I think that's it's also known as Bulletin 17, or sorry, Bulletin 71. Now we're going to talk about sort of the updates, and we've kind of went through this just now when I went through the kind of the some screen captures of the website for NOAA Atlas 14. But in that NOAA Atlas 14, you can also get a methodology, and we'll kind of go through that a little bit. All right, so what is the Huff distribution? This is a it gives you a accumulation of, or it's a percentage of the time, this percentage of the rainstorm, and it's based on whether you're going to have a first quartile, second quartile, third quartile, fourth quartile storm. And all these mean is that if I have a first quartile storm, that means the majority of my rainstorm happens in the first quartile. And you can see in this here for a first distribution that 60% of the rain is already fell by the time I get to 25% of the time. If I have a second quartile storm, you've got most of your rain happening in the second quarter of the total rain. By the time I get between 25 and 50%, you can see that I've got 41% of the rain fell in that second quarter. Here, 60% of the rain in quartile one storm, quartile 2, 41% happens. That's the largest quartile in the second quarter. Third quartile, same kind of thing. Look, third quarter being the biggest amount of rain, and here it's 40% happens, and you can see the rest of the quarters they're much less. And then a fourth quartile storm basically is going to be in the most of it happening in that fourth quarter. Obviously, rain that's fell on all these. All right, so here we've got 49% happening in that fourth quarter. So what's that look like in terms of making a decision? And what the recommendation is that in 6 hours, use a quartile 1 storm. If you get between 6 and 12 hours, use a quartile 2. Between 12 and 24 hours, use a quartile 3. And greater than 24 hours, use a quartile 4. And this is kind of goes with the research that they've done. And you find most of these storms that are less have most of their rain happening in the first quarter. These are dominated by thunderstorms, and you can see kind of how that would impact that. when we have rainstorms between 6 and 12%, there's 12 hours, 6 hours and 12 hours, that's dominated by, mostly occurs here when you get to 12 to 24-hour storms, and then greater than that, it's quartile 4. So those are recommendations on how we select if we're going to use a Huff distribution to distribute our rainfall, which one we've used. So let's look at a quick example. And I went on to NOAA Atlas 14, and I selected, as I showed you in the example, I got, for a 3-hour storm, I got 4.21. Then I want to take and I want to distribute that through time. And so because this time of duration is less than 6 hours, I'm going to use a quartile 1 Huff's distribution. So then I pull that down. This is right out of the report here. I'm in the first 15 or first 5% of the storm, which is I've got a 3-hour storm that gives me to 0.15 hours. And I multiply 8% times 4.21, that gives me 0.34 inches. And then I go to the next item, which is 10% of the time. Then I multiply 17% times 4.21, and I get 0.72 inches. Again, this is cumulative. If I want incremental, I'm going to have to subtract one from the other. So this is going to be 0.34, 0.72 minus 0.34 is what? Then if I go through my 15% of the storm, that's 34% of the rain. So 34% times 4.21 gives me gives me 1.43. That's 0.45 for my hours. Then I go 20% of my storm, that's 0.6 hours. You want to get 2.11. And I just keep going through that until I get all the way to the end where I've got 100% of my rainstorm a portion. So that's the example of how to, and all these distribution, rainfall distribution schemes, be it Huff or USDA or the one that you get from NOAA Atlas 14, they're all going to cumulative time and percentage of total storm precipitation as a factor of that percentage of cumulative storm time. So this is one of the legacy methods I've mentioned, and this is going to be where the Pacific Northwest, you're still going, simply because they don't have NOAA Atlas 14 there. But if you look at that in this old legacy method, you've got basically 24-hour storm and 6-hour storm is the way they do it. And then they have a methodology. If you need a different duration than the 6 or 24-hour storm, you would do that. And it goes by type again, but these types, geographic location. So here's my dimensionless time, and this is my proportion or percentage of rainfall. So if I'm in a type 1, let's use a type 2, especially central United States, is here's, you can see it plotted. Here is just sort of the dimensionless fraction of the rainfall. This is the time in hours on 24. And so let's look at this. So here's our map. Here's my type 2. And so, predominantly most of the that, in these areas here, type 3, these are influenced by what? Hurricanes. And then California, type 1, these are different. And then the type 1A, these are all coastal storms. A lot of this is atmospheric rivers that affect these areas. But again, this is a legacy type, and it's the same thing. I mean, you pick your type. If you're up here in the Pacific Northwest, you're either going to be a type A, and you would use either the type 2 or the type 1A. The same way I use the Huff's distribution to get your value of distribution of your rainfall. Now, I out of the National Engineering Handbook, the Hydrology Chapter 4, Section 630, 0.043. This is online in Canvas. I have this. If you go to the syllabus link in Canvas, I give you the resources. You can click right on that and how to get it, because I've got a folder in the files that basically I've organized by each chapter. You'll see these. Now there's 2 chapter 4s in there because they're broken apart separately in the National Engineering Handbook. But the bottom line is, this is what I want to show you, that the study leads to the conclusion that their use be discontinued. They're talking about their use of the legacy method here with the 24-hour and the 6-hour rainstorm. Now they have when you go there's on page 634.51 on how they actually now get a time distribution. So if you're going to use the National Engineering Handbook, and I actually have an assignment in the assignment for this lecture that you go through and do that in terms of extracting it. It's a fairly interesting way they get their distribution. Hour distribution of rain, but they also acknowledge that they've got to preserve in there the 5-minute distribution that that you've got for NOAA Atlas. For the 5-minute data, you've got 15-minute data, you got 30-minute, you got 60-minute. They use all these different durations, and you should work through the process. Go to here and work through this process. If you show up here on this page, and I encourage you to work meeting stormwater ordinance code to design, like stormwater detention basins and subdivisions that we're designing or whatever. There's also, because we know that you're likely not going to use only 24 hours, going to have to extract a duration that's different. Let's say that maybe it's a 2-hour duration that you need, or a 1 hour, or whatever. And so you're going to extract that out. There's an actual example of how to do that starting on page 640, where it says, starts example 4-5. And I've worked through that. And again, I'm asking you to do that as part of the homework assignment. You're going to do these 2 things as part of it. And so, set up a spreadsheet, work through it. I think it's an exercise that'll book, see how they do things. And who knows, I may have this on a quiz. If I look at NOAA Atlas 14, as I mentioned to you, they'll actually give you a distribution of time rain based on where you're at. You notice this is from the previous example where Evansville. You're going to actually click on this supplementary information tab. So here's, if I wanted it tabular, this gives me that table of the NOAA Atlas 14 results. This is graphical. Go ahead and click on this, which is the tab for getting the supplementary information. And specifically what you want is the temporal distributions. And you can choose a duration. They're very limited. I think it's 24, 12, and 6 hours. So I've just asked for a 24-hour duration, and I hit submit. And then I end up getting basically it downloads a spreadsheet for me. And you should read through this. And so what you see here is they will have 4 different quartiles, and they'll explain that in the report. If you actually go for the Midwest, I've actually loaded the Midwest report. Let's see if it's on the next slide. Yeah, you can actually see for Missouri, you can actually download, and I've got it on Canvas. It'll explain in Appendix A5 what these different outputs are in the spreadsheet. But it gives you 4 quartiles. So I'm showing you the first quartile, I'll give you the second quartile, third quartile, and fourth quartile. And that's based on where the storms at the percentage of those reports, those storms that were in the quartile 1, there's a certain percentage in quartile 2. So you can kind of look at how they were broken out in terms of doing things. And then they build a distribution based on a subset of the total data they had that fit the first quartile, and they built a distribution. And you'll notice that it's percent of duration. So it's we're looking at 10%, 20%, 30%, 40%, etc. These are the times. Let's see here. Let me get this straight. This is sort of the time over total time, and that's what this row here is. Okay, so this is like this is a header. So when I showed you the Huffs, they had 0, you know, various things, 0.05, 0.1, 0.15, 0.2. This was for the Huff, right? P over P total. And they had, you know, 0, 0.3, 0.4, you know, it went on like that. And that you had that kind of information. This is kind of organized a little bit differently, where you've got T over T, TD is listed. Values are the P over P total down in here. Now, the thing that to keep in mind here is that this is slid down on me. This should be yellow, should be up in here. But this is a probability distribution in fit, and it'll make more sense when I show the next slide in a second. But this is the median fit. And so this is the median fit for all cases. This is the median fit for just the quartile 1 cases. And so I'm going to have you do an exercise where you're going to, and I'm asking you to use the all cases 50% value. And you'll see this. You'll notice here I'm down on row 65 in the spreadsheet through 674. Here's the quartile 1, then quartile 2, quartile 3. I've just kind of done you get all this on one slide. Now, these, pay attention to 10%, 20%. Look at this next slide. So you can see here is the all cases for this region, and for the 6 hour, let's go the 24 hour duration. Here's the 50%. So that's down to 90%. So, you know, there's a recommendation that NOAA Atlas 14 makes. And when we do analysis, we have to distribute the rainfall out. And so one of the things that we can also do is we can take the outer bounds of these, and we can see which of these outer bounds, as we come up with different rainfall distributions, which may give us a worst case scenario in terms of the flow. If we're trying to design something and we look at the sensitivity of our model, how the rainfall falls in terms of time, we can see that this is going to be a totally different distribution in time of the rain than down here, than down and into 50%. And when they talk about that, this is just sort of a capture out of the volume 2, which covers the kind of the eastern part of the United States. This is what I want to highlight. Users should consider temporal distributions likely to produce higher peaks rather than the 50 percentile median cases, for example. So this is to all talking about, you know, doing sensitivity analysis when any kind of use of data, because we're fitting a statistical distribution. That's not the exact thing that happens, and you have to kind of look at sensitivity in terms of your data that you're using. So it's just a kind of reminder there. All right, so let's, the last thing I want to cover in this lecture is looking at limiting storms. And we talk about the probable maximum precipitation. And this is a concept that was come up by the Weather Bureau because they were asked back several decades ago, you know, 30s and 40s and 50s, you know, I'm talking 1930s, 1940s, 1950s, when we were designing all these large systems, these big, massive dams that were spending millions of dollars. So you've got a big capital expenditure, plus what happens if it fails? You're going to kill a lot of people living downstream because you have this big flood wave moves through more aggressively and higher than any natural flood would ever do. So we want to look at, can we safely design these for anything, and they wouldn't be overtopped and failed by anything that could possibly, what are the outer extremes that could happen? And so Weather Service did, it was the Weather Bureau at the time, looked at atmospheric conditions in certain parts of the country. If we looked at the juiciest atmosphere that we could imagine and we extracted every bit of the moisture out of the atmosphere, which never usually will happen, but it could. And so what would that look like? And so you come up with the probable maximum precipitation, And you can see the various publications. There's various publications for around the country. And let me look at, this is just what you've got for the PMP out of Hydromet Report 51, which covers kind of the Missouri area. And this is for the PMP for a 6-hour, 100 square miles. And so here we are in Rolla, somewhere around in here. And if you trace this line down, you can see that the 6-hour rainstorm is 28 inches. 28 inches. Now, put that in perspective. They're saying that's the PMP for 6 hours when we have an average annual rainfall around 38 inches in the state of Missouri. So depending on where you're at, but that's a kind of a rule of thumb. So you can talk about, we're talking about a lot of water here. Now, the dam safety program in the state of Missouri requires that you use 75% of the PMP to do your analysis on the dam that would determine whether the spillway was large enough to safely pass a storm that would be 75% of the probable maximum precipitation. All right, that's all I've got. So go to doing the homework assignment.